In this video, we're going to look at how to integrate triple integrals in, how to evaluate triple integrals in cylindrical coordinates. And there's actually not a whole lot here that is new. It's more sort of just putting together concepts that we've seen before. So first of all, what are cylindrical coordinates? They are coordinates that are based on a cylinder. I know that is incredibly hard to believe given the name. So what does that mean? So we have seen a cylinder, right? A cylinder here as something which is typically parallel to one axis. And in this case, it is the z-axis. And it is the traditional meaning of the cylinder, which is sort of the right circular cylinder, is what these kind of coordinates are based on. And so they are, if we look here in the diagram, there's three things going on here. There is, whoops, I didn't mean to obliterate that. There is an angle. There's an angle theta. There is a radius r. There's the radius r. And if you just put those guys together in the xy plane, well, those would just be polar coordinates. So r and theta in the xy plane, they act as if they would in polar coordinates. And the only thing that we add in addition to that is a z. And this z is as if it were in rectangular coordinates, right? So if you have three coordinates, you have r, theta, and z, well, that's enough to pinpoint any point in the plane, right? So you might have a point that goes sort of theta in this direction and r in this direction, right? Here's a theta, here's a radius r, and then down to some point z. So those three things together, r, theta, and z, can pinpoint any point in R3. And how do we convert from standard rectangular? Well, the only thing that needs converting is the x and the y, because the z remains. The z remains in rectangular coordinates, and x and y just get converted as if they were in polar coordinates. So it's super simple. It's a mix. Cylindrical coordinates is a mix of polar and rectangular coordinates. That being said, we can integrate over them super simply, right? We don't need to write this down as a formula, because you could kind of just do it, right? You always integrate your z coordinate first, dz, and then afterwards it's polar, right? Polar with the r dr d theta. And so you have your outside integral in terms of theta. You have your middle integral in terms of the radius. And then you have your inner integral in terms of z, the z function bounds, which have been converted to polar coordinates. And then the function of integration f here, f has had the x and the y converted, just like up above. The x and the y, and the z remains in rectangular. So in cylindrical coordinates, the integral of some function f of x, y, z over a solid shape S dv is given by what's in the box here in pink. So let's do an example real quick of that, and we'll see how sort of natural it feels to put the two things together. So this example says, let S be the interior of x squared plus y squared equals 1. And so if we are in R3, the z is missing, which means that this is a cylinder. It's a cylinder that is parallel to the z-axis, right? Parallel to the z-axis. So our solid is the interior of this cylinder that is below z equals 4, and above z is 1 minus x squared minus y squared, which we should remember as a downward-facing paraboloid. A downward-facing paraboloid. Okay, and so we're told that the density of the solid is proportional to the distance from the axis of the cylinder. Okay, let's unpack that a little bit in just a moment, and then we're asked to find the total mass. The total mass. Okay, so let's first of all let's look at our solid. Right, so we said that it was the interior of this cylinder. So there is our cylinder. X squared plus y squared is equal to 1. It is below the plane. Z is equal to 4. And it is above the paraboloid. Above the paraboloid, Z is equal to 1 minus x squared minus y squared. Okay, so it's an object that looks like this. It looks like some of those glass objects that you might see with a big sort of bulbous bubble in the bottom or something like that. And we're looking to find the mass of the object, which is above the paraboloid and below the plane. Given this information, given that the density is proportional to the distance from the axis of the cylinder. So there's two things going on there. We have the fact that it is proportional, and it is proportional to a distance. So let's look at our density function here. This is our density function. Our density function rho, and we're imagining this function in something like grams per cubic centimeter. The fact that it is proportional just means that it is multiplied here by some k, which is called the constant of proportionality. So we have just some constant. That's all that means for it to be proportional, is that it's multiplied by some constant. And then proportional to what? To the distance from the axis of the cylinder. The axis of the cylinder is the z-axis. The z-axis. And what is the distance from the z-axis? Well, that's the same thing in the plane as the distance from 0, 0, right? So that distance to any point x, y, well, that distance there is the square root of x squared plus y squared. And it doesn't matter whether that point is down in the xy plane or higher up, that distance to the center is exactly the same. So from the description, then here is our density function. And so we know that the mass of an object is the triple integral of the density dV over the solid S. So it is enough then to just set up the bounds of this integral and to integrate. So we are going to do, as we have up here, an integral, the inner integral from z equals 1 to z equals 2. No, from z1 to z2. The top z, well, the top z, that's sitting right here. The top z, z equals 4. That's fine. That doesn't change. We don't have to convert that to rectangular coordinates. But the bottom one, right, the z here has to be converted into rectangular coordinates. So here is our bottom z. So we need to convert that into, I think I've been saying rectangular, from rectangular into polar. So 1 minus x squared minus y squared, so 1 minus r squared is our lower bound. So there is our lower bound. Those are z values. From z is equal to 1 minus r squared up to z is equal to 4. Okay, and then our first differential is dz. Now the next thing that we need to do, well, the k just remains, is to convert our function. Right? We have to convert our function as well. We keep any z's, but we have to transform the x and the y into polar. So there are no z's here, right? There are no z's in this function. So we are going to transform that into polar coordinates, which is the square root of r squared, which is r as long as r is greater than or equal to 0. And then we have times r d theta. So we have an r here. We have an r from r dr d theta. We put those two r's together, multiply them, and we get r squared. So there is our inner integral. There is our inner integral. And then all we have to do is figure out what the region of integration in the plane is. And that's pretty simple to do. It's this cylinder here, right? This cylinder here. That cylinder is giving us exactly our shadow region in the plane as well. So we're setting up our cylinder on the unit, not our cylinder, our integral over the unit circle. And so that unit circle is the standard circle and is set up using polar coordinates, right? That is 0 to 2 pi because we want the entire circle centered at the origin. That is, if it's the unit circle, r is equal to 1. We want the entire region, so 0 is less than or equal to r is less than or equal to 1. We take those inequalities and we put them up in the integral, so from theta from 0 to 2 pi, r from 0 to 1, and then we have our triple integral. And then it is just a matter of proceeding as we would with any integral once it's been set up. We start with the inner integral. Well, the first thing I did actually was I moved the constant outside. Then I integrate with respect to z. There is no z in the integrand, so I get the integral of dz gives me z from 1 minus r squared to 4. Right? And then you just proceed. So I have next factored out the integral with a theta because there are no thetas anywhere, so that becomes a constant as with respect to r. And then I go and I do FTC2 here, right? This is just the top minus the bottom for z, and we get an integral here which gives me 2 pi times k. Here we expand and get the integrand that you see before you, and then it's just a matter of evaluating and calculating down the way. I'll let you check the steps here that are done, but the final answer, this is supposed to be a density, so our object or the calculation that we're doing is giving us the mass of the object, and so it really is, it's first step, an integral in rectangular coordinates, second step, a double integral in polar coordinates. Put them together that way and you've got triple integrals in cylindrical coordinates.